So let's start. Let me just start by asking you guys to brainstorm a little bit on um, when you say a model is interpretable, uh, what properties do you think it should have? What would make it interpretable?
The
Um,
outcomes or the predictions are clearly relatable to internal workings or to inputs. Yeah,
Clearly
we can trace the processing
to
and
internal
understand it.
structure. Okay. I mean, that's in some ways also true of just even a generic machine learning um, algorithm, in that you can perturb, that's what they do with what they call explainable AI. They just do sensitivity analysis. You perturb something and see what happens. And in that sense, any database model, like a autoregressive moving average model, is also, the outcomes are relatable to the components, the structure. So there must be something more than that we're wanting or hoping for in an interpretable model. In other words, another way to think about it would be what makes a so-called physics-based model interpretable, or is it not? Maybe we don't agree.
so I think, if you talk about physics itself, they are obeying certain laws and that you clearly can see in the model.
Okay. And these are encoded clearly,
Encoded
clearly in
clearly,
the
right?
model. Okay. Model structure. Okay.
And I would say that the learned parameters have to be somewhat meaningful.
Okay.
So when you have too much equifinality in even a simple conceptual model, it's not really interpretable if the parameters that you're learning are meaningless.
Okay.
It has to do with identifiability and stuff.
We're
And
not
maybe
saying for notes anymore, or at least
sorry
the notes aren't. You're
again.
if you're taking new notes, we're not saying new.
Yeah, the whiteboard is not working, Hoshin. It stopped working
Oh, okay.
after a certain point.
Okay. I'm sorry about that, guys. I don't know what to do, short of restarting my computer. But yeah, let's just talk about it. If I could just pick up on what Joseph said, um, talking about the parameters, maybe I could generalize and say the structures or the features internal to the model are meaningful in some sense. Would that make sense, Joseph? It's not just parameters, but any
Yeah, both. Yeah.
internal
Full
component.
system identification is kind of
Right.
unique and meaningful.
Okay. So in other words, one way of saying that is you can relate each of those internal components to something in the real world, accepting the fact that that relationship is conceptual, right? Because the relationship's happening in our mind, in our head. But we're taking the real world and we're sort of abstracting it in terms of concepts. Then we want our model to have components, features, parameters, whatever, that are somehow relatable to those. And what that makes me think of is some of the ML stuff that they were doing with generating art, where they were building the models in such a way that you had knobs that you could turn. And so you could turn one knob and it would change the perspective on the image, and another knob would change the color and the hue, the degree of saturation. One would make it more realistic and less or less realistic. In other words, there was some kind of independent degrees of freedom that were represented somehow internally, and then those ended up being knobs that you could turn, right? Something like that. Would you
Hoshin, I
agree
think,
something
yeah,
like that is true of our physics-based models too?
yeah, I was gonna say that the perspectives that Laura and Joseph gave us um, maybe are complementary, because one is distilling distilling the knowledge from the data through laws, which is the physics. But what Joseph said is we all agree that there may be some equivalentity, and that doesn't actually mean that they are not interpretable, because you can always interpret things in multiple ways.
So you're saying the equifinality may be a consequence of identifiability problems. That doesn't necessarily mean that it's not interpretable.
Yeah, that's correct. You can interpret a problem in different ways, and maybe some ways take more energy than others to interpret, or more bits. Maybe, but they're still interpretable even by the human brain. But some of the features may be correlated or associated, and there may be a combination of features that are the simplest way to explain the things, and that would be kind of a law, which would be kind of the most beautiful way to understand a problem, the simplest way.
And I would argue the laws are also concepts. They're ideas that we
Yeah,
impose on the world, whether
yeah.
they're real or not is I'm not debating that.
Exactly. Yeah.
But
So
I
yes,
like
sort of first degree approximations to something. That's right.
but I
Or
like
second degree.
the point that you're making, which is that equifinality, should distinguish between being able to assign meaning to being able to identify precisely what the values are. And so there's a distinction somehow between equifinality and between whether something is interpretable or has meaning in some sense.
Yeah, I was actually arguing the other direction, so that
Okay.
Non-identifiability implies not interpretable. But I do see Herman's point. So I would say that, interpretability is on a spectrum. If we gain some identifiability, that definitely makes the model more interpretable, but it's not maybe necessary. Maybe not a necessary condition for interpretability.
Sure.
And also, I'd like to point out, you mentioned that, the parameters have to have real world meaning. But I just want to comment that we even struggle at the moment for hydrological parameters to have kind of mathematical meaning as well, because if you simulate streamflow data from HBV and try to recover back the parameters from the ground truth HBV model, we still can't do that.
Right.
So even
So,
in
yeah.
mathematical sense, it's not, meaningful.
So I'd agree with you that perhaps ever since we've been building models, there's been a sort of a holy grail, or physics-based model. There's this sort of holy grail of this idea that we can build models and that everything in the model will be identifiable and interpretable. But arguably, we've been struggling with that for my entire career and longer than that. All right. Any other thoughts or suggestions?
So something that occurred to me from my physics-based background in fluid dynamics is that you may need to have certain control over the model. So for example, if you need to impose the boundary conditions, the initial conditions of the model, that will make the model interpretable, because you can interpret it. You can interpret the model from the physics itself, including the boundary and initial conditions.
So what that's making me think of is that one thing that nobody's mentioned is that we typically think of our models as being somehow representable by equations.
Mm-hmm.
And those equations typically use particular operations that we have decided on as having meaning to us, like sine, cosine, logarithm, multiplication, division, addition, raising to a power, and so on. And equations are compositional, right? So equations, and then they're compositional. And I think this will come back when we start thinking about cans. But equations can involve differential equations, integral equations, things like that. So there are concepts about states and rates of change and so on, which are very endemic to dynamical systems. And even if there are no states and no rates of change, if you're just doing regression, you could say y is equal to log of x squared or something like that. And you somehow have in the back of your mind some understanding or interpretation of what that means because you can graph it and you can say that this value relates to this value through some operation or transformation or something. So it seems to me that that's an important part of interpretability. And of course, you could argue that just doing linear affine transformations and passing through activation functions is also something like that. But somehow what happens is when we build physics-based models, we tend to build them as modular in some sense, and using these components that we can assign meaning to in some sense. And if there are too many bits and pieces, or if we can't chunk up so that we can hold a small number of pieces in our minds, then we have difficulty interpreting them. Yeah. So if I give you something with 100 or 1,000 or 1,000,000 moving parts, and I ask you interpret this for me, somehow you're going to chunk it up to something which has only 4 or 5 or 6 or 7 components. So there's this sort of hierarchical, compositional nature of things. Does that sort of make sense? In other words, any physics-based model I can think of can typically be written down as a set of equations. And before we had computers, we would write those equations down and we would try to solve them using mathematics. And if we couldn't solve them using mathematics, we'd hire a computer, which was a person, and we would come up with some approximation schemes for doing calculations, and we would run calculations and we would document them. And then when computers came along, we used computers to do mechanical and digital devices to do that for us somehow. And so even if we couldn't tell you what the outcome was going to be, we could run it computationally into the future using something. And then we look at the results and we would say, okay, that helps me understand what's going on. Yeah. And so typically when we look at models and we're interested in whether they're reasonable or not, Yang has alluded to this in some of his work, we'll say, well, if I change this thing, I would expect this other thing to change in this way, because if I increase precipitation, I would expect stream flow to go up. If I increase temperature, I might expect stream flow to go down. Things like that, because although we may not be able to say precisely exactly to what extent. Okay. Any other thoughts about what interpretability means?
Along those lines, can you say that the model is going to depend on the level of expertise of the person who is building it?
That makes
So it
perfect
has
sense.
certain it has certain constraints in terms of the interpretability, and sometimes it's not transferable to other environments or even from person to person.
So a good example of that was that back in 1984, 1980s, when I got started on this, National Weather Service had an expert by the name of Eric Anderson, who did all of their flood forecast model development using the National Weather Service model. And it's still around, basically. Anderson and a bunch of other people, Bernash and Farrell and others who developed it. And Anderson was the one who calibrated that model to every watershed around the country. It took him something like 20 days per watershed, I believe. But it's because he understood the model. He understood what the internal components, how changing something would create a change in its behavior. And when we came along and started posing automatic calibration, we sort of, in a way, we did something which helped speed up the process, but it took away that intuitive understanding, interpretability part of it. And then, of course, ultimately led to notions like equifinality and so on, because now we're concerned about how precisely we could pin down the parameter values from data and so on.
I have a question, if I may. Do you consider interpretability as a sort of like discrete category, or are you thinking about like a continuous, like a gradient of like there are degrees of interpretability for models?
I think you're implying that that's reasonable, and I would agree. So interpretability is partly, I think there's some dimensions here about complexity is certainly one of them. Representability using a language which I can understand is another one. And familiarity with that language is certainly true. So if I'm not familiar with Chinese, the language might be interpretable, but not by me, right? But to an expert native speaker of Chinese, it would be perfectly interpretable. And I've heard people argue that machine learning models are perfectly interpretable by people who understand the language of machine learning. And it's hard to argue against that. So I agree. It's sort of a lot of it has to do with this notion of interpretable by me or by some reasonable expert with a certain level of training. That certainly seems to be part of it. Okay, let me put some thoughts and we can come back to that. Can you see, you can't see my screen, right? Let me shift back to, can you see my PowerPoint now?
No.
Okay.
That's still on the iPad.
How do I stop sharing? There it is, I found it. And now I'll start sharing on my screen. Can you see my PowerPoint now?
Yes.
Okay. So here's some thoughts I wanted to bring forward. Hopefully this will work. I thought it'd be useful by just talking about the geoscientific problem, just as have some kind of basis of agreement as to some of the things that we agree on. Well, we can talk a little bit about the basic structure of physics-based modeling, the basic structure of modern machine learning modeling, some more recent work from CAN theory. We've talked about CANs before in this group. I think there's some relevance from ideas from information theory, information bottleneck. I think there's some relevant points which come up when we talk about the lottery ticket hypothesis. Then Yang presented Han's work on pruning quantization and IT coding. I think that's interesting. I put this other one in red because I'm not sure we'll have time to get into that, but I do think there's some relevant things from all of our work that could be brought to bear, including Jan's MCP, Luis's regional hydro LSTM, and others. And then I kind of have a bias towards the work of Stanley et al., who's a roboticist who has been working on this notion of neuroevolution, which is a different way of developing and training neural networks from the classic way. And if we have time, I'd like to spend a little bit of time explaining what I think his ideas are there. Something called compositional pattern producing networks, why those are relevant, the development of that into something called hibernate, and then some more recent developments. In a sense, pointing towards a direction that I suspect modern machine learning is going in or will be going in. And I think as we as a group in the geoscientific community, I really think we need to be aware of this, because I think these are things that are happening and they're beyond what we are typically giving attention to. And I think they're important. So if we just start with the geoscientific problem, we talked about understanding interpretability and its relationship to language. I just love this little quote by Galileo. The universe is written in mathematical language. Its characters are triangles, circles, and other geometric figures, without which it's impossible to understand a word. Without these, one is wandering in a dark labyrinth. And I'll just point out that when we say triangle, we've agreed on the meaning of this structure. What does it mean? What does it look like? What are its properties? When we say circle, what are its properties? When we say sinusoid or logarithm, what are its properties? So these are things that, these are concepts or words that we have generated and agreed upon as a community. And even though we might not have 100% exactly precise agreement on the meaning, because I don't know what's in your mind, you know what's in mine, there's at least enough agreement that we can have a conversation. Some of you may have seen this before. Here's what I think of as the goal of science, at least from an information theory perspective. And it's to discover a representation or to develop a representation, including its embedding, that is interpretable. We've discussed a little bit what do we mean by interpretable. That is of minimal complexity. I don't think that's completely well defined either, but you can think in terms of descriptive complexity. How many symbols do you need? Computational complexity, how much computation does it need? There's various dimensions of complexity, I think. And the point of the representation is that it results in minimal predictive surprise. In other words, it represents the world well enough that we can use it to predict things, typically, not always. That we can use those concepts or the model to generalize. It's got good generalization ability when tested against reality. And the last one I added recently, supports and facilitates scientific reasoning. And one of the things I've been looking at with my colleagues here at the U of A is, what the heck is reasoning? What is hydrological reasoning? When we as educators train our students, presumably we're training them to somehow be able to use what we've taught them in some context to do reasoning. And so what are the elements of that? Yeah. And so I would say all of these, but particularly interpretable, supports, enables reasoning. So there's this element. And what is reasoning? Reasoning sort of involves being able to represent the world in terms of symbols, which you can then manipulate and move around. And when you manipulate them, move them around according to some grammatical rules, they give results which are consistent and realistic in some sense. Yeah. So if I add two numbers, it gives me a result that is consistent. If I divide something by something else, it gives me a result that's consistent and has some kind of meaning to me. Just keep stopping me if there's any discussion at any point. Yeah. I want to point out that generalization ability is not that simple. Typically, we want to generalize in time and space, some kind of stationary conditional data generating process. And you could say the easiest kind of generalization is interpolation, means being able to predict what's happening within the range of some training data. And then you can talk about generalization extrapolation, going beyond the range represented by the data that you might have, but still being able to rely on it and trust it. And I would call these, this is just my own terminology, I'll call these first and second order generalization ability. So in the beginning, what you do in machine learning is you get some data, and what you're really looking for when you separate into train and test periods, or train, select, and test periods, is you're really looking for first order generalization ability. You're saying, if I were to take this model and use it with data that comes from the same sort of data range, it's going to behave in a way that's consistent with how it behaves when I trained it on this data. And that's what I would call first order generalization ability. And there's been debate in the hydrologic literature as to, because people like Klemesh and others wrote things which said, no, that's not, we want generalized outside of the range of the data. We want to generalize to other catchments, to what happens under temperature change or climate change or something like that. And it's arguable whether there's any way to test that, right? Because you're saying I have to generalize beyond the range of the data, but I don't have the data. If I had the data, I would train it with all the data. So then how do I know it's going to work well outside of the range of the data? And so you end up with this catch-22 kind of a problem. Then you want to be able to generalize under structural change. So the first is nothing is changing. It's just in the range of the data or outside the range of the data. But then you want to be able to say, hey, if the world changes, I want to be able to change something in my model. And so therefore my model has to be interpretable in some way, so that if the world changes, I have something in the model that can also be changed, which represents that change in the world. And then I can tell you what's going to happen under those conditions, right? So this is predicting outside the range, not just of the data, but also conditions which generate that data. So it changes structural form and algorithmic complexity, and I'd call that third order generalization ability. And it's sort of like we'd learn the laws of hydrology, and then somebody wants to apply them on Mars, right? So presumably many of the basic laws of physics and science apply on Mars too. Presumably some of the basic laws of hydrology apply on Mars too. And then we want to be able to do maybe a higher order generalization ability. And this would be to isomorphically similar systems. So the system is not quite the same, but I can somehow generalize my representation to another thing, to another system, which let's say has similar dynamics or similar structure or something. So similar in some ways, but dissimilar in others. And so this is sort of in some sense the holy grail of the entire modeling process. That's my thought. Okay. So that's my take on, when we talk about generalization, we're not very clear, but I think of it as being at least in these four senses. Any reaction or thoughts on that? Okay. I would argue that when you're just doing interpolation, in some sense, there's no need for interpretability, although you might like it, right? And then as you go further and further down this chart of levels of generalization ability, I would argue that the need for meaningful interpretability progressively increases. Okay. And in some sense, we can also relate this to intelligence. We think of people as being intelligent if they can do these kinds of generalizations. Yeah. Okay. Okay, so the general problem is we want to somehow learn both from data and theory. We want to construct representations that characterize system dynamics, since we're interested in dynamics. We want to be able to use them to generalize across space and time. For example, catchment scale prediction, characterize dominant processes, learn a generic enough representation of catchments from many, many catchments, regionalize, generalize to predict under changing climate or land use, and then interpretable to support decision making, because ultimately these models get put into some kind of decision analysis context, and the stakeholders need to be able to trust that model. It needs to be credible and salient. And then you're going to run that model, make simulations, and they're going to say, well, what would happen if I cut down all the trees? Or what would happen if I built a dam over here or something like that? As human beings, we want to engineer and modify the world. And if the model is not interpretable, we're going to have difficulty being able to use it in this kind of decision-making context. Okay. So we want to be able to reason about causes and potential behaviors under alternative conditions, what you call scenario analysis. Some desirable attributes: they should be learnable. They should be regionalizable or generalizable, transferable is another word. In other words, I like this idea of like, you might have a category of cats or catchments, and you have types of cats or types of catchments. So you have different types of dynamics, and you want to be able to classify systems into systems with different kinds of dynamics. Interpretable, what does that mean? Is it the same as explainable? I'm not sure. What's the relationship to reasoning? Yeah. And of course, for a representation to be interpretable, I won't spend a lot of time on this. We talked about this already. Must be based on a language that somehow makes sense, which means an alphabet, a dictionary, a vocabulary, grammatical rules, and so on. Facilitates abstraction. And so any description constructed using that language should in principle be interpretable by me, as long as I am an expert in that language or sufficiently familiar with that language. And that's why you get into these arguments between machine learning people, I think, and physics-based modelers as to which one is interpretable. It really depends on your point of view, I think. I'll also point out that the choice of embedding is important. What's an embedding? It's a particular choice about how to represent or encode relevant information, right? It's a particular choice about what to represent and what symbolic language to use to represent it and what grammatical rules apply. And we particularly choose our embeddings because if they don't facilitate computation, then they're not going to be useful to us. So they have to facilitate reasoning or computation or something. So we choose our embeddings to be able to do that. They should be able to facilitate some kind of a similarity assessment. In machine learning, the typical choice of embedding is vector space operations, right? So it's particularly apparent in transformers that take word tokens, represent them in vector space, and then do an embedding where certain operations on those tokens translate into mathematical vector operations in vector space. Okay, so you can assess similarity by vector dot products, and then vector addition and subtraction correspond to operations that have semantic meaning. And word token order can be provided by doing modifications. Those can be doing vector modifications and so on. And the reason I mentioned that one is just to point out that there are other kinds of machine learning, graph neural networks, that need to perform operations on different kinds of objects, not just vectors, so nodes and edges. And they then require a different kind of vector space embedding. So if you dig into graph neural network theory and you look into see what people are doing there, they point out that some of the standard operations, vector space embedding operations, don't necessarily work for graph neural networks, and they have to invent new operations and new ways of designing those embeddings. And you could argue that our choices about how to build a physics-based model is a kind of embedding. It's a choice about an embedding, okay? A language and a set of rules. And then I just put this one up because I wanted to sort of highlight the difference between different kinds of network architectures or system architectures that we could. So the one on the top left is supposed to represent a kind of a physically based system architecture where you've got states, which are representing nodes, and then you've got gating operations, which are your flux operations. And then you've got connections, which indicate pathways, flux pathways. And then you've got some kind of architectural arrangement there, which has been chosen in such a way as to have meaning. So water flows into a tank and then it flows into another tank, bypassing a third tank. But in the meantime, there's a bypass. And so you've got all these kinds of things. Yeah. Down below on the bottom, you've got the classic machine learning architecture, which is fully connected layers of nodes and links, and which has become very popular and very powerful. And then the third one I want to show you over there, which is interesting to me because it's sort of a hybrid in some sense between the two. And this is the kind of architecture that can be developed using neuroevolution, which is the thing I'm trying to get at. And you can see that it still has features or nodes, but you'll notice that the nodes are not connected quite in the same way that they are in the fully connected deep neural network. You don't have a clear notion of layers. You have something that looks like layers, but not necessarily clear. You know that things are connected in more complex fashion and a lot more like my understanding anyway is how neurons are connected in the brain. Okay. And there are channels and then things are connected and so on. And then these colors represent different kind of functional behaviors. If you change things that are in the green boxes, they have a particular kind of effect on the output. If you change things that are in the brown boxes, they have a different kind of effect on the output, and so on. And you can see the similarity of the analogy there to the physically based models. But as you can see, a lot more complex in some sense than the physically based models, but still there's some kind of modular, hierarchical architectural structure. And what I want to suggest by the end of today's discussion is that to me, this looks like where we should be going. Okay. But maybe not. And I'd be interested in your opinions on that.
Hoshin, let me
Yes.
just interrupt you for a moment and just an analogy. I think the evolving architecture kind of resembles a little bit what's going on with the skip connections in the CNNs that kind of direct the attention on purpose to favor relationships among some layers and others not so much. But I guess the point you're getting at is that this should be giving us insights into the interpretability more than just creating or calibrating the skip connections themselves.
That's a very good point. And if you look at some of the CNN architectures, you will see that they also look quite a bit like this. They've got multiple pathways, and then you've got, what are they called?
The inception, I guess.
Inception
model.
modules.
Yeah.
Right?
Yep.
Yeah. So you see this kind of idea in that and in residual networks and pathways and so on and so forth. And I would not be very surprised to learn that much of the very high level neural networks that are being developed by OpenAI and all these things have architectures that in some sense resemble this thing now. So, I mean, there's stuff that's going on that we're just working with the very early primitive stuff, and there are people working on much more advanced things. Yeah.
I have a question when you talk about these spaces. Can we fully characterize the space in which these networks are operating, the landscape, the mathematical landscape? Can we fully understand the paths that they are taking to generate those outputs? Because if we cannot, then there's a limit to that idea of interpretability.
I think there's always a limit to the idea of interpretability because you could argue that you could develop a machine learning artificial intelligence which I can't understand, right? Just like I cannot currently understand what's going on under the hood of my car. But when I was growing up, I could go and take a class in mechanical engineering, and I could learn how to work on the engine and all its bits and pieces. But now it's gotten to a level of complexity where I would have to go back to school, and it's not even sure I would still be able to understand it then. And certainly, if you ask me to explain all the parts that went into building the Apollo 11, I don't think I could do that, right?
Yeah, but in principle, because it was built, it is interpretable.
So in principle, everything is interpretable, but
because it's operating in a space that we understand. I mean, when you're building the car and when you're building the rocket, you are still constrained by the laws of physics and math and chemistry and electronics. But when you have a system that is operating in a space that is mathematically abstract and is not subject to all these constraints, your interpretability can vanish very fast.
Well, first of all, interpretable by who? Yeah. So there are mathematicians who work with mathematical languages that I don't understand, but they do. You could also say that when Einstein came up with his theory of relativity, or when they came up with quantum mechanics, there are people who still claim that it's not understandable by them. So I think you're asking a question to which the answer would be you can always get to some level at which any individual cannot interpret it.
But it's interesting that you bring the example by Einstein, right? Because what I understand is that he had to play in this other geometric place to finally kind of like free himself from how we understand space and time. And then in that geometric space, he found that relationship and curvature, and then that's how but even that space was constrained by the observations, by the observations that Einstein was trying to solve about that what was happening with light. So that space and the way that he played in that space was constrained by an observation from the real world. But in a neural network, you don't have an ability to constrain the space that you're going to explore internally, mathematically. We can approach it, but it has so many dimensions that how could you argue that there's an element of interpretability when they can go in directions that we cannot even understand beyond the theoretical aspect of math. Like there's no mathematical expert that could even get to understand those spaces that they might go to solve a problem.
So let me first let me just clarify something from you. If you're talking about neural networks which are only using linear affine functions and rectified linear units, that's one class of neural networks. Okay, fair enough. With dot product operations and a fixed set of operations. You're saying that even in that case, because of dimensionality, you lose interpretability at some point?
Not right, because in those ones, if it's a simple, and as long as you can characterize the space in which the operations are happening, I think you have interpretability. But you also mentioned, for instance, like what the OpenAI is doing. There is no way to mathematically characterize the space that those models are moving through.
I'm not sure if everybody agreed with you on that, but somebody else had something they wanted to say.
I want to chip in that it's always a matter of abstraction, because I came to this thought with this discussion, but also when the example of the car was dropped. With a modern car, I'm not sure if there's anybody out there who can really understand all the details of how it is constructed, how it functions, like every single moving part there. There might be some like outstanding geniuses, but like there's equally like problems imaginable that are not understandable at all for individual people. But the point is that a car is not made by an individual people, by one individual person. It's like a group effort. It's like things are built in society between people, like in a group, in a corporation. Knowledge is acquired in society. So there's experts who know things about individual aspects, and you can, sticking with the car, you can understand how the car works depending on the level of abstraction you look at it, right? So and the same applies for these methods that we are looking here. Just today I was with a student, I was having a discussion about performance metrics, and there was a time when Pearson correlation coefficient or Nash subdiff efficiency were cutting-edge research. There was research on it, that people were like thinking for years about these things. There's like, it's not really research today anymore. We just apply it, like we maybe don't even understand the individual reasons why this performance metric has this kind of form. So it's like the same. And then with these models, they were developed over decades, and yeah, there were reasons why they were designed like that, to be interpretable for them and all that. And nowadays we have these composites, these like transformer is like a composition of different elements, right? You can understand it at a level of abstraction, and then if you dig in, you can learn individual aspects. But there's a limit to what you really can interpret as an individual, I would say.
And
So
probably we can
depending on
also,
the level of abstraction.
and probably we can also agree that we can understand or interpret things at different levels. So
Yeah,
I
but
can understand a car just at the level of being able to drive it, but maybe not at the level of being able to fix the engine. Yeah.
but all
But
those forms of interpretability are epistemic. Like what I'm hearing is like
Absolutely.
we cannot. But what if there is an element that is a structure, like the fact that we know that mathematical systems cannot be closed. There's always going to be a gap, and these systems are not operating in a physical space. They're operating in a mathematical space, and we also know that in mathematical spaces you can have emergence, complexity. So there are things that can happen under the hood that structurally are uninterpretable or uncertain, I would say. So there is an element of interpretability that can be defined as epistemic. The problem is that we don't have enough information, but if we could, we would get the full interpretation. But there is also a structural dimension of that interpretability that could be elusive, that we can't just not get it, not because we don't have the knowledge, but just because the structure of how the system is working.
Fair enough.
so
Joseph, you're a
I want
mathematician. Can I ask Joseph if he has any comments on that?
so I want to raise one question here. So interpretability could be something that the human brain can do by hand, or even, like when we talk about physics-based model, you can actually resolve the equations and write them down. But when you cannot control the calculations that the neural network is doing, or any type of MLP, then we can say we are losing interpretability because we cannot control what is happening inside. I'm not sure if that's true from the point of view of architectures.
Well, everything that you guys are saying just highlights for me the fact that the word interpretable is not precisely well defined yet, at least not for me, right? It's one of those abstract terms like love or happiness or whatever, the intelligence, where we're still struggling to. Intelligence is a good one because they keep trying to define intelligence, so at what point does a machine become intelligent, right? Luis?
No, what I was thinking is that really for sure, this kind of space that we are working is not completely clear, but there is always a level of interpretability or kind of constraint of this space that you can add. Because for me, the classical example was this kind of machine learning model that were creating faces. And I remember when, 3, 4 years ago, they were creating faces, they couldn't control the, different features in the face. The nose, the eye. And suddenly, in some moment, they were able to say, okay, maybe now I can add a glass. Now I can add that. Now I can control something. And basically, yes, they're controlling some part of this latent space, adding kind of constraint. And this constraint now is adding kind of interpretability. For sure, this doesn't mean that they are understanding exactly all the kind of operation or kind of the weights that are inside, but in an overall sense, they are adding this kind of interpretability of this model. So it's a level. What level you want to go with interpretability? Something that is kind of give you the chance to control or understand, or you want to understand to the level that I want to understand why this weight in this part of the network is this value and not another one. This is kind of a completely different level of interpretability.
So I think Luis is pointing to something which I want to focus on. There are many dimensions, and that has to do with how we choose the embedding or the representation of the latent space. And we do it in a particular way. And when we do it in a particular way, we get a certain kind of interpretability. But we can choose a different kind of latent space embedding, and we get a different kind of interpretability. And this points to the fact that there's no, in some sense, there's no single correct way to represent a system. There's no correct model of a system. The model is always driven by our goals in some sense. Yeah. Yeah. All right. We can keep coming back to that, but that's a long subject, as we can see. Let's just be clear about the structure of traditional physics-based modeling. So physics-based models are typically constructed to represent dynamical flows of mass, energy, and information. We use symbolic language, so they can be typically expressed using something like differential equations or difference equations. And visually, using visual language, we represent them using directed graphs. Yeah. So if you want to explain a model to me, if I say, explain to me this thing, you'll draw me a picture. And you'll say, it has these components and these things connect to these and these things, that's at least how we talk about them. They also go through certain sort of stages. I use this in my classes. We have a physical system. We have some prior understanding of that system. We have some data. And we start with some kind of informal perceptual conceptual idea as to what's that system, which is always driven by the goals or the idea why I want to build that model. So if I'm looking at a watershed and I'm a geologist, I'm going to build a different kind of a model than if I'm a hydrologist, or if I'm an artist, or something else, or an ornithologist, or something. And then we build a conceptual model from that. In other words, we choose some symbolic language. We impose conservation laws. We make some choices about system architecture, what state variables to represent and what's connected to what. Then we impose some mathematics on that, some formal mathematics. We come up with a process parameterization or a gating function hypothesis. And then what Joe was referring to earlier is that the model, when you have the equations have parameters, which allow you to tweak them and move them around. But we want those parameters to be somehow related to physical properties of the system, material and geometric properties typically. You can abstract this to other kinds of systems. And so if we change a parameter in a model, we want it to relate somehow to something that could have been changed in the physical world. Okay. And then we code that up, we get a computational model, and we go around this loop. Yeah. And if it doesn't work, we just keep going around and around, trying to improve this. Whereas in a machine learning model, we might still start with a perceptual conceptual model. We choose some kind of, at least now, and I'm hoping this will change, select some kind of suitable machine learning architecture. So we make some kind of system architecture hypothesis. Are we going to use linear affine functions and fully connected networks and rectified linear units, or what are we going to use? And then we code that up, and then we go around the loop. And there's sort of a step we bypass, which is typically, but not always, that step which says that we got to obey certain physical laws or principles. So whereas back here, we might be working with flows of mass, energy, and information, here, typically, we're more working with flows of information, although we could impose regularizing constraints to distinguish some of those kinds of information as big mass and energy and momentum and so on. So we got a perceptual conceptual representation using mental symbols, got a conceptual representation using pictures, words, and numerical symbols. Then we get a mathematical representation using equations, and then a computational representation, so we can do computation, modern computation. And then we end up with architectures like this. And the thing I want to point out about this is that there's very clearly a sort of a modular compositional nature to the construction. We build it up in modules. We choose modules that have particular meaning. We assign meaning to those modules. we constrain them to have certain kinds of behaviors and so on, and then we build them up. Okay. On the other hand, you could look at the structure of modern machine learning-based modeling, and the archetypical example is something like this, which is a fully connected set of nodes and links, where you have certain operations on the links, you have certain operations on the nodes, and you just put them together. And then you pass your data from inputs to outputs, and then you'd use backpropagation backwards to train the parameters, use differential programming to be able to train this model, so to speak. And so a standard neural network architecture, let's say I've got a 2-input, 5 hidden unit, 1 output multi-layer perceptron might look something like this, where you take the inputs, you multiply them by some weights, you take the other input multiplied by some weights, and then at each of the hidden layer nodes, you do some addition operation, some kind of linear affine transformation, and then you pass it through an activation function. And that ends up being some kind of a feature. I'm going to call this H. And then you take those features and you do some kind of linear combination, typically linear combination of those features. It doesn't have to be linear. And once again, you add them together. So you use superposition, and then you possibly pass them through an activation function. And so that's just a cartoon, okay? Things obviously can get a lot more complicated than that. And you can write out the equations, and you can look at it and analyze it and so on. So the idea being that you've got learnable weights, but typically you fix the operations. You don't learn the operations, although in some more advanced things, you can actually even try to learn the operations. And then, so you can think of this as sort of a regression problem. You got some inputs, you got some learned weights, you do nonlinear affine transformation, you do a bunch of these, you end up with features. And then you take those features, and you got some learned weights, you do another affine transformation, you go to an output, and you got various kinds of activation functions that you can use. And it's fairly obvious now, I think, why we typically use something like a rectified linear unit, because any nonlinear function can be approximated as a piecewise continuous set of linear pieces. And so in a sense, it's not difficult to see why you would do that to get a kind of a universal approximation. And there might be some kinds of behaviors like abrupt changes and so on that are hard to represent. Okay. But the main idea seems to be, and what makes this so powerful, is that you learn features of the input data. And then the idea is that they can be combined linearly, and that linear combination is what makes it easy to understand, compute, and interpret. If you believe that, except in high dimensions. Yeah. And then, of course, you can learn hierarchical structures by arranging many hidden layers in series. Okay. You can do autoregressive dynamics by making the inputs time delayed in time. So it's exactly the same structure. And you get this time delay neural network where you got time varying inputs. So you end up with time varying features, but you still have fixed time constant weights, and you end up with a time varying output. Okay. That can be combined linearly. And it may not be immediately obvious to some people, but if you look at it closely, you'll see this is essentially a convolutional neural network. It's a time convolutional neural network, yeah? Convolution in time. And so one of the key decisions here is this this time window. How many inputs, time-lagged inputs, can I put in? That's the receptive field. Right, so you have to choose this receptive field, and something similar occurs in transformers, except that the weights are not learned constants, but they are time-varying weights, context-dependent weights. And then you could say, okay, but I can feed back the time-varying feature and say that feature at the next time step depends on the inputs and some fed back value at the previous time step. And so you can do Markovian dynamics. and you end up with something which is Markovian time-varying features that can be combined linearly, and inputs can be lagged or not lagged, and so on. And so you're essentially adding kind of a memory, and recurrent neural networks up to LSTMs are sort of basically versions of this. Okay, and the memory functions kind of like a momentum thing, which says that things don't just depend on the input, but also depend on the state of the system that has evolved. And so if you look at a single node of a recurrent neural network, you basically have these weights, which are learned constants. Yeah, and you have this Markovian recurrent structure. But then you get to LSTMs, and they basically said, okay, instead of, I'm abstracting a bit here, but instead of having constant weights, I'm going to learn gates. So the weights can be time varying, but they're context dependent. So I replace the weights with some functions over there, where the functions depend on the cell state and the inputs and various other things like that. But the architecture is the same. And instead of constant weights, you now have gates. And so you still have this linear Markovian sort of structure to the system. It's just that you don't treat the weights as being time constant anymore. You treat them as gates, which are time varying. And you learn those functions. And then, of course, you end up with two kinds of memory. You've got Markovian memory, and you've got this time delay, contextual memory. And we can get into discussion about various kinds of memory that are in the system. Okay. And so you could see that things become a lot more complicated because the connectivity becomes much more complicated. Things can feedback and affect each other and so on. And arguably, this is what gives an LSTM its power. One of the things that gives an LSTM its power. Then people came along and said, Kolmogorov-Arnold networks, 2 papers came out in 2024, CAN and CAN2. And these are based on Kolmogorov's neural network existence theorem, which basically says that if you've got any continuous function on some closed interval, you can implement it exactly by a 3-layer neural network, where if you've got D inputs, you only need 2D plus 1 nodes in the hidden layer, and you can have C processing elements in the outer layer, and you can represent it using this mathematical form, where it basically takes each individual input, does a nonlinear one-dimensional transformation on that input, sums up those transformed values, passes that summed value through another nonlinear function, sums up those, and so on and so forth. Okay. We've talked about this before. And is non-constructive because it doesn't tell us what these functions look like. We can stick any functions in we want, but it does lead to this sort of popular rule of thumb, which says if you have 2 inputs, then you need something like 5 nodes in the hidden layer. And of course, people don't follow that in modern neural networks. But there's a reason, I think, why this is interesting, because what they basically proved mathematically was that if you could find what these functions psi and phi are, you really only need 2D plus 1 nodes in the hidden layer. And so it put a constraint on the structure, the architecture of the network. Okay. And I think it's an interesting constraint. And in a sense, what they showed was that any multivariate continuous function on a bounded domain can be written as a finite composition of continuous functions of single variables, so mappings from X to Y, one-dimensional mappings, and the binary operation of addition. So in a sense, they showed that the only true multivariate function is addition. Every other function can be written using univariate transformations and sums. And this is a very powerful thing. Okay. So if this is your standard artificial neural network architecture, just the cartoon, 2 inputs, 5 nodes, and an output, the analogy to that with a CAN architecture looks like this. So instead of weights, constants on the connections, you have these nonlinear transformations, one-dimensional transformations. At the nodes, you don't have activation functions. You just have addition. And so now you've got 5, 10, 15 different functions that have to be learned in this particular example, up to 15 different functions. And according to them, according to this, for two inputs and one output, that imposes a maximum limit on how many functions you would have to learn. And then this is the basis of cans. I don't have a slide here, but can 2 then also adds not just addition, but multiplication, because multiplication can always be reduced to taking the log, which converts multiplication to addition, doing transformations on that, and then doing the inverse log or the exponentiation. And so you could think of multiplication as just being a more complex form of addition, which involves nonlinear transformations. But because multiplication is so pervasive, they invented can2, which has both multiplication and addition at the nodes. And so you don't have to jump through the hoops of having to take the log and then do the addition and then do the exponentiation. So I'm not going to spend any time on it, but in principle, that's what that second paper is about. And of course, you can extend these to deep CAN architectures, and you don't have to be bound by the idea of only D nodes. You can extend that. And the point I want to make here is that, in a sense, there's no distinction between a 3-layer CAN and a 3-layer multi-layer perceptron and a 4-layer CAN. So you can imagine that on the first link, you just have a weight and an identity function, and then you're doing addition, and then a weight and identity function addition. So this is basically a CAN architecture, but I'm restricting myself to only linear transformations on the input side. Then I'm doing addition, and then I'm passing it through these nonlinear functions over here, and then addition, and then and then you got this another function. So in some sense, there's not actually a real difference between cans and multi-layer perceptrons. You can take a can and you can rewrite it as a multi-layer perceptron, but with a very specific architecture. And what that architecture boils down to be is kind of interesting, because if you say that I've got a nonlinear transformation that occurs over here, there's a one-dimensional nonlinear transformation. I'm saying that this thing that enters here is a nonlinear transformation of x1. Well, I could just replace that by a small multi-layer perceptron where I pass it through a bunch of nodes where I just multiply by weights and pass through an activation function like a rectified linear unit, and I can get a nonlinear function. And so you could think of each of these as being a small multi-layer perceptron. And then you could see that the CAN is just sort of an extension of multi-layer perceptrons, except that the nodes in this little section are not connected to the nodes in this one, are not connected there. So they're sort of modular. So you've got these little modular operations that are happening through the network, as opposed to the standard multi-layer perceptron where everything is connected to everything else. So it imposes a kind of modular constraint on the architecture. Okay. I'm hoping that's clear, since we talked about cans before, but if not, if there are any questions, I could take them now. By the way, in cans, they use B-splines to learn these functions, but there's nothing preventing you from learning just small multi-layer perceptrons with linear activation functions, rectified linear units, and so on. Yeah. Okay. Information theory, I think the main insight is bottleneck. And the basic idea there is that we have information in X and we're trying to extract from it the relevant information that is relevant to the prediction Y. So I give you precipitation and temperature and so on, and not all the information in my input data might be relevant to the prediction. So what you're trying to do with the neural network or the model is extract only the relevant information and pass it out. And that relevant information is what we're calling the information bottleneck. Okay. So anything that's not relevant should in principle be thrown away. That way you end up with a minimal model. So we take X and we learn a compression, which could be a lossy compression of X, which we call the code. And then, so we do a mapping from X to X tilde, and then we take X tilde, and then we do a mapping to Y. In other words, we take the information in X, which may be represented by a certain code length, and we try to represent it with a compressed code length. In other words, a smaller number of bits. And so you could argue, and you can do that losslessly, so there's no loss of information where you preserve all of the information, but eventually it's quite possible that some of that information is not relevant, and then you might do a lossy compression. Oh yeah, and I just want to point out that the compressed representation, of course, is not unique. And this goes back to our embedding. We choose our embedding because it has a particular meaning or interpretation to us, but there are many possible interpretations, embeddings we could choose that are informationally equivalent. Another term for that is minimal sufficient statistics. So what does that mean? Well, if I want to represent the information in a data set that comes from a Gaussian distribution, I only need to give you the mean and the standard deviation and tell you that it's Gaussian, and that would be the minimal sufficient statistics of that data set. So I can compress all those random numbers down to these three things, the two numbers, mean and standard deviation, and the fact that it's a Gaussian distribution. Okay, I'll skip all this. Oh yeah, and a possible earth science example is you might have a very high resolution distributed system with rain, falling in time and space and temperature and so on. And we might want to just predict a streamflow hydrograph. And you could see the amount of information encoded in the system could be huge, whereas the amount of information encoded in the hydrograph could be quite a bit less. And so we can take all of this and we can compress it down to only its relevant components. These are the features that we need to identify and track how they evolve in space-time. And then that allows us to build this simplified representation, which hopefully is accurate enough, contains only the relevant information needed to predict streamflow. Obviously, we know that we haven't achieved that yet because we can't predict streamflow perfectly, but that's sort of the idea of the Holy Grail. Yeah. So even though the goal is lossless compression, we typically end up with these sort of lossy or over compressions. Okay. Yeah, I like this picture as sort of like saying, I'm trying to represent a bunny rabbit and I can represent it with a huge amount of detail, but maybe I only need this much detail to basically be able to identify that it's a bunny. Okay. Okay. Some other things I wanted to mention. Hopefully you guys are familiar with the lottery ticket hypothesis. This is a paper that came out in 2019, and it's illustrated by this figure here down on the left, where basically they took neural networks, very high dimensional complex neural networks that have been trained, and they showed that so the blue line represents the test accuracy of the model with training iterations. If they trained all of the parameters of the network, okay, fully connected neural network and the various kinds of networks, including convolution and so on that they tested. And the blue line represents that. And then the orange one represents what happened if they, after training for a little while, they pruned away something like 49% of those weights. And then they trained it, and you got that orange line. So you see the performance test accuracy actually improved. And the green one was actually, they pruned away the remaining only 21% of the weights. And After 21%, in this particular case, they went to 10 and 7 and 5, and then performance went down. And the basic point they were making was that there was some sort of need to have very high dimensional representations in the early stages of training, but that that if you then pruned the network, you could end up with a simpler, a more compressed representation, information bottleneck, which actually had better performance than the original because you were not training in a higher dimensional space, you were training in a lower dimensional space. But that there was a limit to how much compression you could do, how much pruning you could do. And you didn't know in advance what that was. On the other hand, if you then pruned the network and then took the pruned network and reinitialized all of the parameters and retrained it, you wouldn't get good performance. Okay. So it was not just an issue of architecture. It had to do with the part of the parameter space that you were able to access because you had a very high dimensional initial parameter space. In other words, it was kind of like doing global optimization. And then you were progressively pruning down into a limited part of that weight space. And because you were pruning down, you're now able to get better, more efficient training, algorithmic training, because the same amount of data was being used to train a smaller number of parameters. Does that sort of make sense? This is one of the things that has been in the discussion of neural networks now for some time. And then similarly, they actually even cited the work of Han, but Yang presented this stuff where he's been working on what he calls tiny ML. And so they use pruning to reduce the number of weights. They use quantization so that they don't represent the weights at high precision. Since they're 64, 32, they might even go down to 8-bit or 4-bit or 2-bit precision. And then they use Huffman coding to represent those weights in a space using a kind of a mapping, which allowed them to reduce the amount of memory even more. And this figure sort of illustrates that. Ignore the green line. So they took a network, and so now the model size after compression. So this is 20% of compression all the way down to 2% compression, meaning 2% means they reduced 98% of the weights. Yeah. And of the amount of storage, memory storage that they needed to store the model. And you could see if they only did quantization, which means they went from 64 to 32 to 16 to 8 to 4-bit sort of precision, different levels of quantization, you could see here's the 0% loss up at the top, and that you could get all the way down to something like 15% of the original model size without any loss of accuracy. And then as you did more and more quantization, you started to lose accuracy at some point beyond something like 11 or 8%. But if you did not do quantization, if you just did pruning, you just took away weights and trained, then you actually got better performance. So you still maintained better performance with lower amount of memory. And if you did both pruning and quantization, so you reduce the number of weights and you quantize them down to a lower dimension, that you could get almost down to something like 3 or 4% of the original model size with no loss in accuracy. So I find this rather interesting because this brings information theory to bear on the whole machine learning problem. And it basically is asking a question which is along the lines of what information do I need to preserve and at what precision do I need to preserve it in the model? And it turned out that certain layers they could quantize more and other layers they could quantize less. And so it's this complex problem of balancing pruning and quantization and so on while maintaining model accuracy. And the reason they're doing this is because they want to be able to run these things on iPhones and so on. So they're taking transformer networks and then they're dramatically compressing them down while still maintaining the performance level and accuracy. Okay, it turns out that by doing Huffman coding, you only need a very, very, the code book actually doesn't take up very much space, so that's not relevant. Okay. I'm sorry, guys, it's already 11:30. I'd hoped to get to genetic coding and evolutionary machine learning. So there's probably something that we should come back and discuss at some other time. But the whole point of this last part, which I'm very interested in, all of this was sort of leading up to this, was to point out that there are methods that are being developed in robotics which allow you to build these kind of networks which have a different kind of architecture, which is more modular and more differently connected, like I showed you in the beginning. Um, and I can see some definite possible applications of these kind of networks and architectures in hydrology. So there's several things, one including NEAT, which is how do you evolve these architectures using evolution. Then there's something called a compositional pattern producing network, which is a way of developing a network which actually has a structure like this, but which has an output in 2 dimensions or 3 dimensions or 4 dimensions, where the output has some kind of structure, which in this case looks like a picture, okay? Why is this relevant? You can see that this picture is very complex, okay? There's a lot of complexity in this art, this image that's come out. But the actual mathematical complexity required to generate this image is actually quite simple, okay? It's just the nodes and weights and what do you call them, activation functions of this particular architecture, this connectivity. And why do I think this is interesting is because if you look at things like hydraulic conductivity fields, they have these interesting structures, okay? There's one example. There's a 3-dimensional example of a geohydrological structure, and you can see that it has structure, right? But what do we do right now? When we want to build hydraulic conductivity fields, we just use simple things like kriging. And kriging is just a simple thing like a Gaussian or some kind of a nugget in a sill in a very, very simple variogram structure, right? And of course, the simple variogram structures can only result in simple conductivity fields. They have to obey those particular rules. And what I see as being a possible interesting thing is that you might be able to build neural networks which are simple, but are much more interesting and complex than variograms that are also interpretable, which would allow you to actually generate fields which are more physically realistic, the kind that we see in the world. And so I'm sort of completely fascinated by the idea that one could actually possibly learn mathematical generating relationships which result in these sort of complex output patterns which are consistent with the kinds of patterns we see in reality. So the basic idea is that this network can generate a field of weights, neural network weights. And those neural network weights will obey certain patterns and shapes. So the network weights are not random now. They're not being trained in some random way. They're actually being constrained by some regularizing principle to obey certain kind of rules, such as might be hydraulic conductivity fields or geological fields, and so on. And so what they do is they train a network, but the network has weights, but they don't train on the weights directly. They output those weights from a compositional pattern producing network. And they train the much lower dimensional architecture and weights of this compositional pattern producing network, like the weights of the variogram, which then generate this high dimensional set of weights of the neural network. but which have some particular pattern which could be potentially interpretable. And that's the basic idea. Okay. And that's what's called hyperneat. And then they go through and show that using this kind of structure, they're able to assign or show that there are structures that emerge in this neural network, which when you perturb them have interpretable effects on the outputs. Okay. So you can say if I tweak this, then it has this kind of effect. It generates a shadow image, or it just generates this kind of a change to the image, and so on. Kind of like what we're doing now with GANs and art and other kinds of things. So sorry, I wanted to spend a lot more time on this, and actually I'd like to come back and spend more time on that. But hopefully I've sort of conveyed the gist of my idea, initiated some kind of a basis for some discussion. All of this leads me towards this notion of learning architectures that are interpretable in some sense, and that the properties of those architectures are things that are modular, compositional. So you can see the relationship, similarity to CANs in some sense, similarity to neuroevolution type architectures, but where from a kind of simplicity, a complexity can arise. And that complexity can reflect a kind of complexity that we see in the actual world. So I will stop there and see if you guys have any thoughts or comments, because I don't want to take too long.
I can't remember if we discussed it or not, but we talked about what the definition of interpretability is, but did we talk about like why we want interpretability, or what we call interpretability?
Maybe a little bit.
So to you, what's the main purpose of interpretability, do you think?
Yeah, let me go back to the early slides. Not sure how to do this fast. Where's my... here we go. I guess for me, it's sort of something along the lines of supports, enables reasoning, but also represents the world at a sufficient level of complexity that representation can result in minimal predictive surprise and good generalization ability. Maybe that's my sort of short version of that, Joe.
Which reminds me that maybe when we talk about physics-based models, not all of them are interpretable. And not only, because what we talk about interpretable to you, but also because you end up in high parameterization of the variables that at the end, you are not interpreting, you are losing the laws of physics once you start lowering down the order of the model. So for example, when we talk about Navier-Stokes equations, you can decompose, the fluid dynamics into or you can solve, the parameters in different ways. Some of them are pretty complex and they are interpretable, but when you end up in things like Manning equation, I will say that is not interpretable because it's a very simple equation that you have a roughness coefficient that is changing in orders of magnitude. So parameters like that become non-interpretable for me. I don't know if that makes sense in the context of interpretability, because what we think is physics-based models versus machine learning models, and we are assuming that all the physics-based models are actually interpretable.
Well, but I think what you point to, I'm sorry to jump in, but what I think you point to there is exactly the same problem with the machine learning models interpretability. And if I'm looking at Hoshin's points, the one that jumps out to me is like generalization, right? When we introduce a lot of parameters, these parameterizations in our physics models, right, we understand that creates issues with how well they generalize, especially out of sample. And I think the same is true with our machine learning models. They're very good at, they have all these parameters, they can learn the patterns, but if we can't really interpret them, we don't really, it's difficult to know how well they will generalize.
Well, I would argue that some people find the Manning coefficient insightful for something. So I would say it really depends on who you're talking to. So if you're talking to a very pure physics modeler, then it doesn't make sense. But if you're talking to an engineer, it makes sense. So it's a really subtle concept. But what, I have one thing to add. Perhaps the interpretability gives us some perception of the complexity of the model of the problem we're tackling. Not even the solution, but the problem we're dealing with. So maybe by running a model and finding that this is the minimum representation, that gives us an idea of the complexity of the problem. And then maybe what we need to classify is the problems themselves before tackling them. So we know how to tackle them with the appropriate tools, to make them as interpretable or as simple as possible, as elegant. It's a huge problem, the interpretability.
Would it be fair, Laura, Hernan, Timothy, would it be fair to say that we have to start with certain basic concepts that we have an intuitive understanding of? So if I say pen, I might show you many different possible, but I mean, without actually showing you the pen, it's sort of hard for us to agree on what I mean by the word pen. All right. And so in Manning's equation, we have this concept of roughness, right? Manning's roughness. And so we need to have an intuitive understanding of what roughness means. And then Manning's equation purports to explain all the different things that affect roughness, so that you can somehow quantify it, right?
Exactly. So it's going to depend on the amount of understanding that you have from the environment. So if you know that you're working in a channel that is it has a heavy vegetation, so you can approximate the roughness coefficient of Manning. But if you don't know anything about the environment, I don't think that Manning equation can be interpretable. So if you don't know what is a pen, but you are trying to approximate a concept or an idea of the pen, maybe you have to end up with very high order equations, like something that can explain you an object, a PD equation, for example, that you can see or understand a volume because you actually don't know anything about the pen. But if you know that it's a pen, maybe you can just draw lines and say, okay, I have one line, another line, and another line that crosses, and just a tip right here, that is a pen. But if you tell me I have an object, then I really need to start with very complex equations. That's kind of my, I don't know, my food of thought. I don't know, kind of my understanding of what you can use in terms of physics that allows you to understand processes. And it depends on the level of understanding that you have already. Your prior knowledge means a lot when we are talking about physics-based models.
This might be a little different from my last take, but I guess maybe interpretability doesn't matter. If we had if we had a model that could do everything, we had one generic architecture that could do everything, perhaps we wouldn't need interpretability. But I liked your analogy to the car engine because it, emphasized the point that these models are built by people working together. They're modular. We need to represent their components in a way that we understand. So in that sense, as long as these models are being built by people working together, we need their elements to be interpretable so we can organize and build them collaboratively.
So you're pointing, Timothy, I like that. We sort of skipped over that. You're pointing to the fact that there's a reason for interpretability involves communication. And the communication can be just with myself. That's reasoning. But when you're building a car, you need to be able to communicate with other people. And so you need a shared language. And so we come up with these concepts that we presumably have a shared understanding of. And if our representation uses those shared concepts, then we can kind of communicate with each other and say, yes, I understand what you mean. But if somebody comes up with a new idea and starts using a word for some concept that has not been mutually agreed upon by the group, then you could say, I don't know what you mean. It's not interpretable.
Two things. One is I would say that good generalization ability more or less has nothing to do with interpretability. I mean, to me, the human brain is probably the least interpretable thing on the planet, maybe, and it has very, very good generalization capability, and there's probably other examples as well. And the second point is in response to Dr. Hodson. I sort of agree that maybe interpretability doesn't matter as much, but the problem is I'm writing my thesis right now, or dissertation, and I have one big chapter about building interpretable models, and right now I'm trying to write the conclusions section about kind of implications and significance. So I don't know what to put for that part. I'm a bit stuck about why people would care. I think it's cool and it's good for hydrologists to play around with, but does it have meaningful uses in the real world? I'm not sure.
So are you arguing, Joe, that if you can build a model, going back to something I think Tim said, that is so accurate that under whatever circumstance you apply it, it verifies well. Uh, that even if I can't understand, it's sort of irrelevant. All that matters is that it works.
Well, I think it's at least arguable. I'm not sure if it's true, but
Because I think that as human beings, we like to imagine what would happen under alternative conditions that may not have ever been experienced. I would argue that's part of our human intelligence, part of the reason why we've risen to the top of the food chain.
yeah, but if you have a perfect model that generalizes perfectly, then you have those answers, right?
Yeah, well, maybe the fact that
For some reason we want to be able to say, why does it do that, right? I mean, why is a big question we like to ask.
and also I think because of the no-free-lunch theorem, basically saying that this is not possible, this is why we need interpretability, because that's some hypothetical all-know model that we'll never reach, technically.
Antoine, go back to the free lunch theorem, because wasn't there a paper which basically implied that the problem with the no free lunch theorem was that it was trying to apply to everything? And they were saying that if you just restrict yourself to the universe that we live in, then the no free lunch theorem is not a problem.
Yeah, something like that. Also, they state that the no-free-lunch theorem for AI has not exactly been proven nor that well defined. So there is a certain extent to which the no-frillinge theorem can be applicable to AI models, especially machine learnings and neural networks. So all this is, I guess, all this has to be discussed too. It's not all verified, but I think it's an interesting approach. If that universal omniscient model shall exist, maybe yes, we need not interpretability, but is that the case?
So my problem with the universal omniscient model concept implies that there is a correct um, um, microscopic, not microscopic is the wrong level. There's a correct foundational level representation of the universe, which is universal and the only way to represent the universe. It's kind of like the physics holy grail, which says, everything's made up of atoms, and then it's made up of subatomic particles, and then it's made up of strings. So there's a kind of a religious aspect to that belief system, which says, yes, it exists and we can find it. And I'm not sure, because it's not clear to me that representations are that there is a single correct representation, because I think representations are abstract constructs.
So, in another note, I think the need for interpretability is for us as humans to reconciliate AI with the human knowledge, everything that we have written in the last, I don't know how many years, 3,000 years, from the ancient civilizations to right now, and to kind of like to give value to what we have done so far, which is one way to interpret reality, but it is a very, very good one, because we build out this civilization based on that knowledge. So I think that the pursuit of interpretability is a good one, is a good question, but it probably is not mutually exclusive with the construction of better models, because you can always do a combination, a good model and a good interpretable model, but they're kind of two separate axes, and we tend to confuse them. And I think both of them are valuable, but we need to perhaps work and to reconcile those axes.
I think what you're
Those
saying
axes
is that these
together, yeah.
I think what you're saying is that these are mutually exclusive, that one does not imply
No,
you can't have the.
I don't think so. It's the opposite. I think they're not mutually exclusive. And let me give you an example. You can have the force equals mass times acceleration equation, which is a very simple, nice equation to represent the gravity, right? The force. And you can also build a very dense neural network to do the same, very dense one, right? And you kind of get better results actually with the MLP than with the equation, or equal results. But there will be different ways to write the equation too. Force equals to mass times the derivative of the velocity divided by the time, or something, or in terms of the momentum.
But
So the point is,
you're talking about two representations of different level of complexity, right? And
yeah, exactly.
what I'm suggesting is, let's say you could come up with a completely accurate model. I might still be interested in the minimal complexity representation of that completely accurate model.
Mhm. Well, the answer should be depends on the complexity of the problem. But some problems are low complexity that you could do a minimum representation easy and have the same accuracy as a very dense MLP. But some problems may be more difficult, like hydrologic model, in which you have to compromise accuracy and interpretability.
But if I could build a model where I did not compromise accuracy, I might still choose the minimal complexity model, the minimal sufficient statistics representation, because it facilitates computation and minimal storage and so on. So there might be a reason why I would still do that. And it need not be interpretable. It just has to be minimal complexity,
Mm-hmm.
right?
Yeah, exactly. Yeah.
But then
Yep.
interpretability would be a third dimension, which would say, I want it to align with my previous knowledge, or
Yeah, no, so because then the next level would be discovery. Once you have you have interpreted to the minimum description and nobody else has done that before, then maybe you have discovered something new. Um, so interpretability is key for discovery, I would say. But you don't need to have it if you don't want to discover anything new. I mean, you just have the algorithm and run it and then prove it and perhaps generalize some things. And but if you don't want to discover anything, that's fine too. In terms of discover a very simple representation that is transferable, and you can write in a book about that, a physics equation, for example. But anyhow, I was going to, before we move into this, I was going to ask for your perspective, Hoshin, into the neural evolution and CAN together. And maybe because you didn't have enough time to talk about it, but I have the feeling you wanted to talk more about that.
we don't have time, but let me just bring up that picture again, because this picture that I used as an illustration to me sort of, I think, summarizes my current understanding of this, or in that saying that we want some kind, we're using nodes and links, we're using a directed graph representation. We want the nodes to be interpretable, meaning we want them to give some meaning, they do some kind of operations. We want the connections to mean something. And then when we put them together, we want the overall directed graph to have certain properties, I think. And those properties are that they're compositional in some hierarchical way, and that they're modular in the sense that you can abstract up. So you could take all of these green nodes and you could represent that by one element and say this is one thing. And you could take all the blue ones and represent that another. So I can do reasoning in the sense that I can move from very fine scale representation to a coarse scale, high level representation and back. And I think reasoning involves that kind of activity. Yeah. And so one of these nodes might represent Manning's roughness, and sorry, one group of nodes might represent Manning's roughness, but the individual nodes might represent all the components that go to affect roughness, right? Or something like that. But I still want to just say roughness, right? Or something like that. And I want it to be minimal complexity. So minimal complexity means as few nodes and links as possible, right? So evolution would evolve a network where if there's a node or a link which is not useful, it would get rid of it. Okay. And then I wanted to evolve structures which then become the basis of evolving more complex structures. That's what they call canalizability or evolvability. So they say that evolution, for example, evolved brains in such a way that your neural networks are bilaterally symmetrical. Okay, so you don't have a short right hand and a long left hand, although there are crabs which have a short right crab and a big left crab. But in general, things are symmetrical. And why are they symmetrical? Because that led to better survival of a species, because symmetry allowed it to run faster or to balance or to do, whatever properties were needed. So that's in evolution, right? That's in biological evolution. So I'm curious about what is this kind of modular, hierarchical, minimal complexity architecture where you can still have some sort of level of understanding and meaning. You can have very good level of performance. You can have good generalizability. It can be the basis of something that's much more complex and so on. But it's a representation which then lends itself to this kind of reasoning process, or what we're calling understanding and generalization and transferability. That's just the direction that this has been taking me in. And whether this is the correct approach to doing that or not, I don't know, but it certainly seems compelling to me. And one of the arguments they make in the paper that I didn't mention is that when they build these very large level neural networks, like transformers and so on, the individual weights, if you look at the maps of them, they just look completely random. But what they have done is they've used this hyperneat algorithm approach to build large language models which have the same level, if not better, performance, but where the weights of the network actually have structure. Okay, they can be represented by these images where saying this part of the component is, this part of the model is doing that, and this part is doing that, and then these links are removable, and so there's at least some supposedly work going on where they're trying to argue that this kind of hierarchical compositional structure is actually a good thing and actually leads to better performance. But that's all part of the debate. Yeah. And I was trying to use the example of hydraulic conductivity fields as the one that I could think of, right? But you could think of clouds. So clouds evolve, and they evolve with a certain kind of structure. And you would want to be able to imagine how that structure evolves by some laws of physics, but there are certain basic properties. And so I think we could, if we start thinking in that direction, we could probably come up with more and more examples of things like that, which this kind of architecture would lend itself towards representing.
This makes me remember the analogy that Pedro Dominguez does in his book of Michelangelo carving the sculpture from the block. Or so in analogy to what you say, would you do this evolution starting from a very dense neural network and then starting to carve out the sculpture, or would you start from the beginning, from 0 and 1 and 2 nodes, and then until you get a complete view? How would you start?
So in the NEAT algorithm, they start from very simple, where you have only the inputs connected to the outputs. And maybe we need to meet again to go over the details of that, because their argument is that you want to build the simplest possible network representation, and you start from simple and you build towards complex because you want minimal description. But it's a moot point as to whether when a baby is born, it's not born with a very complex, fully connected, but obviously it has arc structure, which evolution has evolved, right? And then, I don't know, what happens? Do we lose some of those connections? Do they get repurposed based on our experiences or training in the world? I don't know, but this idea of taking a block and saying, "Oh, um, I see a face in it, so I'm going to now carve out this face." I don't know if that is easier. I've always thought that carving rock is more difficult than building up using plaster of Paris. Does it sort of make sense?
Yeah,
Right?
it does.
When you go to art
Yeah.
school, you take sculpture, but so you either do carving wood, but you also do the other, which is you just put wire frames and you build things up. And it's sort of a moot point to me as to which is actually easier.
So can you say that using NEAT, for example, the neural network is actually interpreting itself in a way that it will evolve, where the processes are more complex and really leave the easier processes in less information or less neural network neurons, for example. So in that way, you actually, the neural network is evolving because it's interpreting the processes.
That would be the implication. And if you combine NEAT with CANs, like Luis is looking at CANs now, in CANs, they say that if the connections are not stronger than some threshold, then they prune them away, right?
Mhm.
So you could imagine architecture is being evolved, but if the connections are weak and not contributing much, then you could have a rule which says throw away this node or this connection. Right?
Yeah, that would be interesting to explore. I don't know if we have any manuscripts on wants and needs together.
Well, Luis has got started on NEAT, so hopefully we'll see where it goes. And I think I have a student over here who's showing some interest in it. So it's not as simple as standard neural networks, just like CANs are not as simple as standard neural networks, because there are a lot of tuning parameters that have to be adjusted. So I think, there's still, I mean, probably the guys who develop it are very experienced and know how to do it, but I think if something else just picked it up and used it, I'm not sure. Luis could probably tell us how easy is it to make it work. Probably it's very easy to make it fail too.
Yeah, really, I have been working that with cans. So, but even cans, it has a lot of tricky movement that you have to do inside. And but it's interesting that in the moment that you are learning all this kind of step that you have to follow, then it's kind of very easy to build up different architectures. But my guess is that every new architecture needs kind of this learning curve that you have to learn. So for sure at the beginning it's hard, but it's something that is possible.
I think what makes CANs interesting is that it reduces everything to one-dimensional functions.
For me, that's beautiful. This is how basically how we are doing all the physics in the world. We are always trying to kind of work in a space that is kind of independent. And by default, CAN is doing that. It's kind of the beginning, I am assuming that it's independent. And then if it's not, okay, you can mix this kind of two univariable in another kind of function and you can continue building up. But the base is that, okay, you're assuming that it's univariate.
And you're basically saying that there is some kind of nonlinear transformation in the univariate space that when you do that transformation, you can just do linear superposition. Right. I mean, that's the essence of the Kolmogorov-Arnold theorem.
Mm.
And so it's a kind of a trick they're applying. They're saying, this is not easy to understand, so let's do this transformation. And now all of a sudden it becomes easy because everything is additive, yeah, when we do that. All right, guys, thank you so much for showing up for this discussion. I really appreciate it. Thanks, Antoine, again, for keeping us